Hey y'all, what's up? You know who it is. Make sure to like, make sure to subscribe, make sure to drop a comment in, ring that bell for notifications, and especially if you want to be credentialed. Okay, in today's talk, we're talking about systems of equations, starting off a new unit, and we're going to explore what the heck is a system of equations and what is a system. We're going to look at how to interpret the graph of a system. Graphs are going to be important in this unit, as well as a method algebraically for solving a system of equations called the substitution method. And then we're going to look with our understanding of a system, we're going to look at some different types of systems that we might have. This is going to be very systematic. I hope your systems thinking is on point. Have I said the word system enough yet? Well, buckle up for the next 20 some minutes. All right, starting off with this problem. I want you to find a solution that satisfies the equation 3x plus y equals 8 and x minus 2y equals 12. Let's take a minute and let's think about what this means. We need to find a solution to the equation 3x plus y equals 8 and x minus 2y equals 12. Take 2 minutes. Try to pause the video and think to yourself, maybe even talk with a partner if there's one nearby, but think, what is it that this word and implies here? I have one equation and another one. I said find a solution that satisfies this equation and this equation. This should look a bit familiar if you remember your algebra, okay? Take a minute, pause the video, think about it, and we'll check back in about 2 minutes. Okay, well, hopefully you had some time to think about it, but if you just skipped ahead, all right, that's fine. Remember that the word and here, when I'm saying I want to find a solution that satisfies the equation 3x plus y equals 8 and x minus 2y equals 12. This equation right here has infinitely many solutions. This equation right here has infinitely many solutions as well. I want to find the solution. Find the solution, and remember, a solution for an equation is an ordered pair xy. Find what combination of x and y you need that is a solution to both equations. So what we're trying to find here is I'm trying to find an xy value that I could plug in to both of the equations and it would work out. I don't want to plug it into just one. I want to find the specific ordered pair or the collection of ordered pairs that if I plug it into plug it into both of the equations, it would work for both. Okay? You might remember this phrasing of the word and that might help us out when we get to the graphing of these. So think back to when did we past use the word and in mathematics? All right, so let's take a second and let's talk about what a system of equations is, get a definition down, and remind ourselves of what we're trying to find here. So a system of equations really is a collection of two or more equations. So I have two or more equations in the same variable working at the same time. By this I mean you have multiple equations going on, and I'm talking like they're in the same variable. They're in x and y. It's not like you have an equation for xy and then ab and then kj and nm. No. We have all of the same variables, right? And they're working together at the same time, meaning that I'm saying all of the equations in the system are related together. Like they're all working at one point in time. It's not like you have one graph of one, you have a graph of the other, and they're like four separate problems. No, we think of a system as one problem. It's a collection of equations that are all together, okay? Now, solutions. We're going to define a solution to a system of equations as a point or points, plural, that are solutions to all of the equations. I'm abbreviating EQS here for equations. So a point or points that are solutions to all of the equations in a system. So I'm trying to find ordered pairs, things for x and y. Maybe I have one, maybe I have a multiples in a set. But what I'm trying to find is what x, y values are solutions to all of the equations. I'm not trying to write all of their solutions. I'm trying to write the coordinate points that I guarantee are solutions for all of the equations. Meaning you take a coordinate point and you plug that same coordinate point into all of them and it will work. So let's talk about the graph of what's going on here. Let's get kind of an image for what this graph might look like. So I could be kind of having a rough sketch here. This first one, 3x plus y equals 8. If I put that in slope-intercept form, it's going to have a y-intercept up here at 8. It's going to have a slope of -3, so it's going to be kind of steep, come down like this. And then the x minus 2y equals 12. If I solve it for y, it's going to have a y-intercept of -6, and it's going to have a slope of 1/2, so it's going to be a little less steep. So there's kind of an image for what's going on. I'm going to use Desmos to get a more accurate image, though. So taking a look at Desmos right here, I've entered into Desmos.com under their graphing option. I've entered in both of the equations, and we get this nice graph. We can move it around, take a look at it. The red one is 3x plus y equals 8. The blue one is x minus 2y equals 12. And we need to ask ourselves, what is the point or points that's a solution to both of these equations? Now, all of the solutions to the blue equation are right here along the blue line, right? All of these infinitely many points are solutions to the blue equation. And then all the solutions to the red equation are right here on the red line. Everything that passes through that red line. So if we're thinking to ourselves, how can we go about and find a solution that works for both? What value would we say is a value of x and y that if I plug this into both equations, it's going to work out? Pause the video, take a minute to talk with a partner or think about this individually, but what's going on here? What point on this graph would be this magical XY point? What point on this graph is a solution for both of the equations? Pause the video, take about 2 minutes to think about this to yourselves or with a partner. All right, well, hopefully you had some time to work this through, but it might be kind of obvious, and that maybe not, but if we look at the graph here, we can see that this point right here, this coordinate point right here, is the XY value we want. This point right here, notice that it is in the red set, it's on the red line, and this point is also on the blue line. That means, because we said any point on the graph is a solution to the equation. That means that this point right here, this xy point, this ordered pair right here, that's a solution to both the red and the blue equation. Do you see any other points along the graph that are solutions to both? No, because there aren't any. There's in fact just this one point, this one spot where the two graphs intersect. You might notice again how we phrased this problem at the beginning. I'm trying to satisfy this equation and this equation. Remember that word and references intersection. So I'm taking the intersection of the two solutions, right? I'm taking all the solutions of one, all the solutions of the other, and I'm looking for their intersection. So really, I'm looking for where the two graphs overlap. So switching over to Desmos, if I was looking on here and I wanted to take a look at that intersection point, it looks like it's 4, -4. Thank you, Desmos. 4, -4 seems to be that solution point that we are trying to figure out what it is. So let's go ahead and write that down. So this solution point is 4, -4. So if I plug this point into both of the equations, it should work out. Let's test that. 3 times 4 plus -4 equals 8. That's 12 plus -4 equals 8. Hey, that works out. Let's test the other one while we are here. 4 minus 2 times -4 equals 12. So let's see, that's 4. -2 times -4 is positive 8. So 4 plus 8 equals 12. Hey, that works out as well. So this point is our solution for -4. Now the trouble is I don't want to have to graph these things every time. You know, maybe I don't have Desmos with me. And what if the intersection here happened way off in the x-axis, somewhere in like the hundreds or the thousands? We need to have a different algebraic way of going about solving this. So this is where we get into the substitution method. If we have the problem 3x plus y equals 8 and x minus 2y equals 12, we need to think of a way of solving this algebraically. So that way we can solve any system algebraically. Well, there's a couple methods, and the first one that we're going to talk about is called the substitution method. This is a very popular technique. What it says is you have two equations here. Pick one of them. So pick one equation and pick a variable in the equation to solve for. It does not matter which equation you pick or which variable you solve for. Just pick one. So I could solve this one for x or y, and I could solve this equation for x or y. So I'm going to pick the easier one. I'm going to take the equation, and I'm going to do this in maybe blue. X minus 2y equals 12. So then x equals 2y plus 12. So I took the first equation and I solved it for x. And you might be saying, okay, what good does this do? Well, notice now that I have the equation 3x plus y equals 8. If I went to try to solve this red equation, I wouldn't be able to, right? You're saying, well, there's nothing to solve. You have two variables. You have to get one variable, right? By itself on a side to be able to solve it. Now we have two. So this isn't really any helpful. Take a minute and think. How does knowing that x equals 2y plus 12 and having this equation help you out? And I'll give you a hint. Gosh, it would be much easier if I had an equation of all one variable, like if I had an equation of all x's or all y's, as opposed to two variables, x and y. Use that hint, take a minute, think about the problem, and we'll come back and check our work. All right, well, hopefully you had time to think about it and come up with what the idea here is. But really, what we're saying is, okay, if I have the equation 3x plus y equals 8, I know what x is equal to. I can change, instead of writing 3x plus y, I'm going to write 3 times what x is equal to. This is x. The variables aren't different, they're the same. So go ahead and plug in 2y plus 12 plus y equals 8. All we did here was we substituted in what the variable was equal to, okay? We have a system. We're trying to figure out where they give us the same answers. So, to do this, step 1, you pick an equation and you solve for a variable. Doesn't matter what equation, doesn't matter what variable, just pick one. Then, you take the other equation and you plug in what that variable equals. Then you just go ahead and solve it. So let's distribute this. We get 6y plus, 3 times 12 is 36, plus y equals 8. So that's 7y plus 36 equals 8. Let's go ahead and subtract 36 from both sides. So 8 minus 36 should give me a negative 28. So I have 7y equals negative 28. So y should be negative 4. Hey, I just figured out what the y value has to be. So we solved everything, we figured out what y has to be. But now, remember, we have to find an ordered pair, so let's now go and figure out what x has to be. Okay, well, that's easy. I know that x equals 2y plus 12, so x equals 2 times negative 4 plus 12. Let's see, that's negative 8 plus 12, which equals 4. So my answer should be 4, negative 4. And it is. It matches the graph, and we just did it algebraically. This is the idea with the substitution method, how we go about doing this. We can talk about a process for this, and we said, step 1, pick an equation, doesn't matter which, and solve for a variable. Again, does not matter which. Pick an equation, solve for a variable. I'm going to say substitute in, if my stylus works, substitute in what this variable equals into the other equation. That was an important step where we take, for example, we solved for x and we plugged what does x equal into the other equation. So pick an equation and solve for a variable, then sub in what the variable equals into the other equation. Step 3 will be solve for the variable. So actually figure out what that number is. Before we solved for y, we found y equals negative 4. So solve for the variable. And then step 4, solve for the other variable. Okay? That was a big step. A lot of times people tend to forget this. So first we had pick an equation and solve for a variable. Second step we had, all right, plug what that variable equals into the other equation. Step 3, solve for one of the variables. Step 4, solve for the other variable. I can't tell you how many times people forget to do that. They solve for y, but they forget to solve for x. So solve for that other variable. And then, this is just more so for me, write your answer as an ordered pair x, y. So there we go. That's our process for how to go about and perform the substitution method. Now, that works with systems, but we keep talking about systems and we're looking at a specific type of system, but really recognize that there are multiple systems out there is going to be very helpful to us going forward. Now, there's some wording that we use to describe systems. First, we talk about whether or not a system is consistent or inconsistent. Now, a consistent system has a solution. That's what consistent means. It gives you a solution. There's a solution to the system, right? We can solve for an x and y. An inconsistent system does not have a solution. Okay? So sometimes maybe our system doesn't have a solution. Maybe there's no spot, no xy value that works for both equations. That can happen. Then let's talk about dependence versus independence. Now, a dependent system is basically a system where the equations are the same, or at least a couple of the equations are the same equation. It's almost as if I wrote the equation twice, okay? That's what a dependent system is. An independent system is all of the equations are unique, meaning they're their own, okay? They're not the same. They're different. So we have consistent versus inconsistent. That talks about whether or not there's a solution. And then dependent versus independent talks about how are the equations related to each other. So if we take a look at a couple of these graphs, we can see, okay, here's a situation where there is one unique solution. It's right there, right where our two graphs go ahead and intersect. So I'm going to go and say that this system for the first part is consistent. It has a solution, but I'm also going to say it is independent. Obviously, the two equations are not the same. One's going in one direction, one's going the other. So this is nice. This is a consistent and independent system. Now let's look at problem number 2. This one's a little weird. This says there's no solution. There is no point that satisfies both equations. Well, that means that these lines are parallel. That means they're never going to intersect. If they intersected, that intersection point would be a solution to both of the equations, but it's not. These two lines are parallel. They'll never intersect. So, do they have a solution? No. So this is going to be inconsistent. So this one is inconsistent. But are the two graphs the same or are they different? Well, the two lines are different. They're plotted in different areas. So it's still independent. The system is going to be independent. Now let's take a look at infinitely many solutions. This is where I have infinitely many intersection points. So I have a line on the graph, and then I draw a second line, or I write a new equation. You'll notice I just drew that line on top of the other one. So this is a system that is consistent. Okay, it has solutions. In fact, it has infinitely many solutions, but it is also dependent. Because really what I have here is the same equation. It's not different at all. We have the exact same equation. Maybe it looked differently. Maybe one was in standard form, one was in slope-intercept form. I don't know. But really all we have here are the same equations, one line on top of itself. And in this way, we get infinitely many solutions. So really be able to recognize these different types of systems, and they'll help you kind of determine what the possible solutions might be and how many solutions there are going to be, okay? Now, as always, if you like the content in this video, make sure to like, subscribe, drop a comment, ring that bell if you have any questions, comments, concerns, or if you're just like, hey, your talk was awesome, you're pretty awesome, then hey, go ahead, feel free to let me know. Drop a comment, or if you have any other questions, feel free to send me an email at klinford, that's KLINFORD, at wccnet.edu. As always, hashtag Linford for life, hashtag Wrath of Khan, taking them down one video at a time, hashtag Khan, I'm coming for you. All right, take care, y'all.